Hey guys, it's Jesse here with another Elevate video. Now just before, we were looking at a simple bomb calorimeter setup with regards to enthalpy. And now we're going to be looking at is something I almost guarantee you will get in your exam, and this is a diagram for an enthalpy reaction pathway. Now again, there's always some fundamental understanding going on behind the scenes, and that's what I think is always important. So what do we need to do here, guys? Well, we need to plot the progress of reaction with the potential energy. And the potential energy is made up of the energy within the system or within the molecules. And of course, hopefully you understand that the progress reaction is what leads us from reactants all the way to products. That's essentially what this little x-axis is talking about here. So on the right-hand side, we'll have our products. On the left-hand side, we'll have our reactants. And that's the reason why is we're actually demonstrating as we go along this reaction what actually happens to our potential energy. Now, we don't necessarily know the starting and finishing points. In fact, in this case, if you read the question, we're not sure where we start or where we finish. But usually the thing we're nearly always told is what's the difference. Now, sometimes you might need to find that from an initial and final condition, but usually you're just told to change. Now hopefully it is really obvious, but that positive energy value of course means this is an endothermic reaction, and in general that means your graph is going to look something like this. Of course, exothermic is the other way around. We're also given an activation energy, and this is the energy required to break those initial bonds. Now, let's have a start off. So we don't actually know where along this y-axis to start our graph, but because we know it's going to go up like this because it's an endothermic reaction, we may as well start somewhere near the bottom. So I'm just going to pick a spot, it doesn't really matter, and that line could be right here for me. And currently, this is the potential energy of both our carbon dioxide and our nitrogen oxide combined together. Now what happens is we've got this activation energy right here, and what that is that's the total energy required before that reaction can proceed. So that means this full rise here is equal to 360 kilojoules. And make sure you indicate that on your graph. If you're ever given values, make sure you draw that. I'll be extra nice to my examiner and even write a dotted line, but if you're running a bit tight for time, of course you could leave that. Now the potential energy is actually going to decrease as energy starts to be stored into some of these bonds, but at some point we're going to have to stop, and we'll make our final line here. And this line is the final potential energy for this system, and that's the energy of the carbon monoxide and the nitrogen dioxide. And of course the difference between these two is simply the difference in enthalpy, and that is delta H equals 226 kilojoules. And again, I'll be nice to my examiner, drawing those dotted lines and make it really clear that I know what I'm doing. Awesome. So I'm basically done now, in theory, aside from the fact that there's a couple things we might have missed if we weren't paying attention. Include a scale on the vertical axis. Critical. If they ask you to do something, make sure you do it. So how do I know what I'm going to start at? Well, it's a little bit tricky. Because I don't have a value to start for here, I'm just going to make my life easy and call this 0. Call that 0 kilojoules. And then, of course, up the top, that means this would be 360 kilojoules. And right here would be 200 kilojoules, roughly. Last bit I asked for, use a dashed line to show a possible catalyzed pathway. Now, what does a catalyst do? Of course, it reduces the activation energy. It reduces this number. It doesn't change in enthalpy at all. It simply reduces the amount of energy required to break those bonds initially. And it does that in a variety of different ways, which can include in conformation and also providing additional surface area. So if all it does is reduces this activation energy, that means that this value right here is actually going to be a little bit lower, and I'm going to pick that spot right there. But it must finish at the same point and it must start at the same point. So I'm going to do a dotted line and hopefully it should look something like that. Now final last point, you might want to add on that plus there just to make sure both you're not confused and an examiner when they're reading it. So pretty simple question, but it's important to understand the fundamentals. Firstly, that this is an endothermic reaction and this is an exothermic reaction. Of course, they both have these humps because they both have activation energies, but one of them starts at a higher potential energy and one of them finishes at a higher potential energy. And it's all to do with how much energy is stored within those bonds. So let's have a look at this next part of the question. How much energy is consumed when 2.5 moles of carbon dioxide is reacted with 2.5 moles of nitrogen oxide? Now, thankfully, this equation is really simple, and we've got a 1 to 1 to 1 to 1 reaction. So we don't have to deal with any stoichiometry. We're not stressed about what's the limiting reagent. It's going to be 1 to 1. So all we're looking at here is 2.5 moles of CO2, and it's the same quantity, so we've got enough of both of these, and we know that it takes 226 kilojoules for this to occur, but we now have 2.5 moles. So simply, the energy required is equal to 2.5 times the 226. And if everyone busts out their calculators, it should be pretty obvious that we end up getting 565 kilojoules. And that's how much energy is consumed. Of course, if we were looking at the other way, how much energy was released, so instead of going from reactants to products, we go from products to reactants, it'd actually be the exact same figure, and that's really important to remember. Now we're looking at what is the activation energy when 2.5 moles of CO2 is reacted with 2.5 moles of nitrogen oxide. Now the first thing that most people would do is go, oh, awesome, energy equals moles times my activation energy, which is 360, but hopefully at this stage you've worked out that's really not the way to do it. Activation energy is constant and is independent of the number of moles that are actually being used. So my energy is simply still 360 kilojoules, just like it was written up here. Fantastic. So I hope that gave you some insight in terms of how energy is taken into a system, how energy is released from a system, making sure that they're the exact same number. And I'll see you in the next question.